And we're back. Welcome back and happy Tuesday. Today, we will continue on with the link layer, but we're going to repeat a little bit about how the link layer forwards a frame off a network. We're going to repeat that because I realized that material about ARP, Address Resolution Protocol, was missing. So before we begin, some administrative bits. The final exam period for this class is Tuesday, the 4th of May, from 10:30 a.m. to 12:30 p.m. During that time, we will have a presentation. Half of you will get to present. The other half will be handing in a recording or screencast of your presentation due to the number of students in the class. And so I will randomly select 10 of you to present at the final exam period, and the other 14 of you will hand in a screencast. All right. Also, the final exam presentation slides should be submitted the night before, Monday, the 3rd of May, at 11:59 and 59 seconds. And that is the case if you have a screencast or if you have the slides you're going to be presenting. The final project will be due on the last day of finals, which is Friday, the 7th of May, at 5 p.m. Please note this down on your calendars, smartphones, what have you, that it is not 11:59 and 59 seconds. It is at 5 p.m. sharp. Okay, so why don't we begin? When we last left off, we talked about the link layer, and then specifically we talked about the MAC address. And we didn't talk about ARP, so that's what we will talk about now. The MAC address is a 48-bit address, and it has meaning on a network, on a broadcast radius, so to speak. Now remember, a network is a communication medium over which all of the hosts or end systems can communicate with one another without the intervention of a router serving as an intermediary. And so this MAC address is local in scope, and it takes form as a hexadecimal number, so this is base 16, and each digit represents 4 bits. So we have 8 bits here. We have, let me set my pen. So we have 8 bits here, 8 bits here, 8 bits here, and then another 8 bits, 8 bits, and 8 bits. 8 times 6 is 48. And so this represents your MAC address, and this MAC address is used in the frame header information, and that's how a network card, a link layer, knows that a frame is destined for it. When a MAC address is put out on, when a frame is put out onto a communication medium, the destination MAC address is checked by each link layer, and if that destination MAC address matches your own, then you know that the message, the frame, is intended for you. And so we contrast the MAC address with the IP address, which is 32 bits, and the 32-bit IP address, the dotted quad we talked about, is global in its scope. It uniquely identifies the interface card regardless of what network that it's on. And the router uses the subnet portion to determine out what link, using the forwarding table or the flow table, out what link this datagram should be forwarded. And so where does this LAN address or this MAC address exist? Now, each adapter, network adapter on your local area network has a unique LAN address. And so here we have 4 hosts, each one of which has a network adapter. And these network adapters could be wired. They could also be wireless. Regardless of if they're wired or wireless, you'll notice that these hexadecimal numbers representing 48 bits for the MAC address, they're unique for each one of these host interfaces, these adapters. And so the MAC address is allocated and administered by the IEEE Institute for Electrical and Electronic Engineers. And if you wanted to manufacture your own network cards, you would buy a portion of the MAC address space in similar fashion to how you'd buy a subnet. Now, of course, this MAC address acts like a social security number. It uniquely identifies you to the local area network. And this MAC addressing scheme is a flat address scheme. And this gives it a kind of semblance of portability. In fact, if you have a MAC address and you're on a network, it's very unlikely that someone with the same MAC address is going to be on the same network. But you can move your interface card, your LAN card, from one LAN to another, and that MAC address is still valid. Now, of course, when you manufacture MAC addresses, you're not going to send the same two network cards with the same MAC address, because it could happen, to the same location. No. But you have a portion of your MAC address, the first three pairs of hexadecimal digits, which corresponds to the vendor, and then the second three is uniquely identifying the MAC card or the network card by that vendor. And so if you ever go into Wireshark and you'll notice how it can identify an Apple network interface card in the link layer or an Intel, it's because of those first three pairs of hexadecimal digits for that lower 24 bits of your MAC address, the upper 24 bits. And so that's how they know. So let's take a look at our network again. And one of the questions that you might ponder is, how do you know the MAC address of another interface? Well, you plug yourself in, you know your MAC address, and the MAC address is used to get a frame to another interface card on the network. So how do you know all those destination MAC addresses? Well, that's where the IP address comes in. You can certainly acquire the IP address from another host, and you can do that by looking up the host name and using the DNS resolution to get the IP address. Absolutely, you can get IP addresses. So once you're armed with an IP address, okay, well, how do you send a datagram to that machine? How do you send ultimately a frame? Because it's a link layer. We deal with frames, and the frame's responsibility is to encapsulate a datagram as well as add some header information. So it's made possible by something called Address Resolution Protocol, or ARP. Now, ARP acts just like DNS. It builds a table, and the entries in this table map between, in this case, for ARP, IP addresses and the corresponding MAC address. In the case of DNS, you had a domain name mapped to an IP address. In the case of ARP, you're mapping IP addresses to MAC addresses. And of course, these records have an expiration date encoded by the time to live field. And so when you plug a network card onto your local area network, it's engaging in this ARP, and the result of this engaging the ARP, asking who is IP address, for example, 137.196.7.78, it gets a response from that host that has that IP address, and that response contains its MAC address. And once you get that response from ARP from other hosts on the same network communication medium, you then populate your ARP table with an entry. So now, whenever you need to send your frame to another machine, you are armed now with this table, and from the correct entry in the table, you can now insert the right destination MAC address. Of course, you already know your own source MAC address because you know your own MAC address. The card is installed right there on the same host. All right. So now, let's say some host A wants to send a datagram to another host B. Now, B's MAC address is not known. There's no entry in host A's ARP table. So what does A do? It says, okay, well, it sends a broadcast. Now, when you send a broadcast on a local area network, it has a special MAC address. And it's the MAC address with all Fs, so that corresponds to a 48-bit MAC address that has all ones for each position. And so when you send a datagram or a frame to this broadcast MAC address, every single node on the network, their network interface card, link layer specifically, is going to pick it up. And so whenever it broadcasts that, now everyone sees, okay, well, host A is trying to find out what's the MAC address corresponding to a particular IP address. specifically in this example, the IP address for host B. So now B gets this ARP packet, and it says, oh, wait a minute, that's my IP address. So then it responds to A. How does it respond? It responds with its MAC address. And so then host B then sends a frame to A's MAC address using point-to-point communication via unicast. And so the broadcast is just for the query, but the response is via specific unicast. So when B responds back to A, B addresses, the source address is B's MAC address. The destination address is A's MAC address. And it got A's MAC address when that query went out. And so when A gets that response from B, it then saves a copy of B's IP address along with that response for B's MAC address and puts it in the table as an entry. And then that entry persists until the time to live has now expired. And ARP is a so-called plug-and-play protocol because you don't have to do any special configuration. You just plug in your network card and it builds these ARP tables. And in fact, there are command line tools you can use to display the ARP cache or the ARP table. So let's take a look at how this addressing occurs when you're trying to get a frame to another network. Now, of course, if you're trying to push any kind of packet from one network to the next, you're going to need a router as the intermediary to store and forward that particular packet. Now here we have two networks. We have host A, or network on the right. This is the 111.111.111 network. And then we also have this network on the right. The 111 network is on the left, and the 222 network is on the right. We have subnet 222.222.222. Now, one of the things to observe is that each of these networks on the left here and on the right, they all share the same communication mediums. Therefore, they're in so-called broadcast radius. They can all see one another's messages, and they can all communicate without the intermediary being a router to get those frames from one host to the next. Same thing for this network on the right-hand side. Now, as you can see, then, the interface of the router in the center, it shares an interface with this network on the left, and that router also shares an interface with this network on the right. So this interface card for the router on the 111.111.111 network, it can see all of the traffic. It is in broadcast radius of all the other hosts on this network on the left-hand side. And so it has a MAC address. Now, of course, let's say A wants to send a datagram to B, and B is on this network on the right-hand side, the 222 network, we'll call it. So what does A do? Well, A knows the destination IP address for B because it can do a DNS lookup. A also knows the first hop router or default gateway, which is router R. And so because it knows router R's IP address, A can engage in ARP and know and learn and add an entry to its ARP cache or ARP table, an entry that maps this router's interface on the 111 network to the MAC address for this interface the router has on the 111 network. So A has a mapping just from engaging in ARP that tells it how to get frames to this particular interface on the left-hand side for this router. And so A then knows the IP address of the first hop router. Okay. It then addresses the first hop router to get that datagram to the router. Okay. So it constructs the datagram with the source and the destination IP address. That destination IP address is 222.222.222. That's the destination IP address for that destination B. And so the next thing it does is, okay, where am I going to send it? I'm going to send it to my default gateway. So it encapsulates it with MAC addresses, and this MAC address, the source MAC address, is A's own MAC address. The destination MAC address is going to be the MAC address for the first hop router. So it looks up that first hop router's MAC address from its ARP table, and then it tags the destination MAC address in that frame with the MAC address of that router's interface on the 111 network. So then A puts that frame into the network, and it goes on the wire. The router's interface sees that it's the destination MAC address for its MAC address, so it picks up this frame and strips out the datagram as payload and then sends it up the stack. Now, once it gets to the network layer for the router, it sees that the destination address is 222, repeating, which is B's IP address. So then it says, okay, well, I'm going to send that out a particular output port based on the forwarding table if it's traditional routing, or the flow table if it's software-defined networking. And so once it does that, sends it back down the stack, encapsulates it, and then, of course, the destination MAC address, it looks that up, and it inserts for destination MAC address the MAC address for host B, so that when it sends it out onto that network on the right, it goes on that medium, shared medium, and then B sees, oh, wait a minute, that destination MAC address is my MAC address. Let me go ahead and pick that up. It removes the datagram as payload, sends it up to the network layer, has the port number, and delivers it to the application above. And so this is our sequence about how frames are forwarded from one network to the next, and all hinges on these ARP lookups in combination with the forwarding table or the flow table lookup. All right. So now we'll look at Ethernet. And Ethernet is the dominant wired LAN technology at the moment. That could change maybe decades from now or what have you, but it is at the moment. Now, of course, you can get Ethernet implemented in a single chip. You can have it very, very fast. And it is the first local area network scheme that became very widespread in its use. It's simple, and it can also be made very cheaply. Now, of course, it's kept up with making things fast. You can get Ethernet that's 10 gigabit, 1 gigabit, and in fact, 1 gigabit to the home is not uncommon these days. And so this is the original drawing of Bob Metcalfe's Ethernet sketch. And when the early days of Ethernet were in play, they had different types of topologies, or how you can interconnect the hosts on the network to one another. One popular one was the so-called bus-based topology, and with that you had a coaxial cable, and each one of the network cards physically tapped into that coaxial cable. Now, of course, when they were all trying to communicate at the same time, this caused a collision. And then another topology that became very popular was something called the hub and spoke, and later called the star topology. And the star topology prevails still today, with a little bit of nuanced introduction of a new piece of hardware, something called a switch. And so this is the star topology, and with the star topology, all of these Ethernet cables came to literally the connection of conductors to one another. But this also caused collisions. And so the switch was invented to solve that issue of having multiple hosts trying to communicate at the same time. And so what this Ethernet frame structure contains, when you encapsulate your payload, this is our payload, this is your network layer datagram, you have a preamble section on your Ethernet frame, and the preamble's whole purpose is to synchronize the clocks between the sending Ethernet card and the receiving Ethernet card. And so this preamble has a series of byte patterns, so-called marching ones pattern, 101010, and this 10 represents a plus 5 volts or 0 volts logically in base 2 binary, but it's used to power a clock, to actually synchronize them together. And so the two clocks between the sender and the receiver need to be synchronized in order to say, okay, here's the next bit, here's the next bit, here's the next bit. So we have our preamble, and then we have our destination MAC address. So these are MAC address, that's 48 bits. And then we have the source address, that's a MAC address, that's also 48 bits. And so we have the preamble, which does the synchronization. We have the destination, the source MAC address. And then we also have our payload and our cyclic redundancy check. Now, of course, this type field looks and identifies the higher layer protocol. Now, of course, for the most part, it's IP, but there are other proprietary network layer protocols. Apple Talk is one of them for allowing Apple devices to talk to one another. And so this is our Ethernet frame, and Ethernet is connectionless. There's no handshaking between the sending and receiving network interface card. So NIC stands for network interface card. So there's no establishment of connections. It's unreliable. If the receiving NIC does not send ACKs or NACs, so there's no reliability. Data that is dropped is recovered only if the sender uses a higher level protocol, like reliable data transport that we saw in TCP. Otherwise, any dropped data in terms of a frame is lost. So it relies on the upper layers to fire timer in the case of transmission layer and initiate a reset. And Ethernet, to access the shared media, the MAC protocol, it's unslotted, so there's no reservation of epochs in time or frequency bands, and it uses carrier sense multiple access collision detect using a binary backoff of the same sort that we talked about. And so there are many different Ethernet standards, and these differ by the physical medium as well as the speed and some of the framing techniques and hardware that are used. And so there are different physical media layers. You can have wireless, you can fiber, you can have cable even. And so these things are different based on the material as well as the speed. And so copper pair twisted wire, you can get 100 megabit, you can get gigabit copper twisted pair these days, category 5 or Cat 5 cable, Cat 6 cable, and then you also have the fiber physical layers as well. And so when you look at the naming of the different Ethernet cable standard, look to both the speed as well as the medium. And so let's take a look at these new devices, these switches that grew out of the star topology for the link layer. And so a link layer switch is a so-called layer 2 device because it deals with the physical layer and the link layer and nothing else. And so what the link layer does is stores and forwards an Ethernet frame. It deals purely with layer 2 constructs. But unlike a router, a link layer switch is invisible to all of the network cards. They have no idea that the link layer switch is there. So what does this switch do? Well, it examines all of the incoming frames, and it looks at the MAC address and does selective forwarding from one outgoing incoming link, an ingress link, to some egress link, some outgoing link. And so it does that when a frame is to be forwarded on a particular spoke in that star topology. It uses carrier sense multiple access to access a particular segment. And so a frame comes into a switch, that's the symbol for a switch, and then that switch, based on a particular port, is going to use carrier sense multiple access collision detect in order to put that frame on that particular segment. So what ends up happening is that because the switch effectively probes each one of these spokes separately using CSMA-CD, you don't get any collisions on a particular spoke in this hub and spoke topology. So if you have a host A here, for example, and a host B here, all of your potential collisions are now eliminated. Moreover, with an Ethernet switch, you can have concurrent communications happening. And let's say we have host A here, and it's sending a frame to host B. At the same time, you have host C up top trying to send a frame to host D down below. You can have this A to B forwarding of frames and the C to D forwarding of frames happening concurrently with no collisions. And these switches are plug and play. They're self-learning. So based on the MAC address that's in the source MAC address and the destination MAC address, it populates a table that acts like a forwarding table, but this is a forwarding table based on layer 2, i.e. the MAC address. Okay, and there is no routing that happens in switches. They do this by just recording information, and we'll explain what they mean by that. And so a switch allows multiple simultaneous transmissions, and if you think about it, if you don't have any collisions, now you can have many more hosts, and you can also send much more quickly because you don't spend all this time probing and backing off and probing and backing off. You just send, no collision. And so hosts have a dedicated direct connection to the switch, and when you buy a switch, it'll tell you how many ports you have. And typically you can buy a 4-port switch, you can buy a 6-port switch, an 18-port switch, 24-port switch. They can be rack-mounted, they can be desktop, all sorts of form factors for switches. The switches will buffer the packets, and then the Ethernet protocol is used on each of the incoming links, but there are no collisions. It's full duplex, and each link has its own so-called collision domain. There's no collisions because there's only one host on each one of these links that come together to the switch device. And so a switch also performs what's called switching. It kind of sounds like routing, but it's called switching because these aren't routers. They deal with MAC addresses for the switching decision. And so you can switch from A to A prime, and here we have an example switch for a single network. So we have A prime, B prime, C, and C prime. You can switch from A to A prime frames and from B to B prime at the same time. And the reason for that is because of the combination of the buffering and the selective forwarding. So there are never any collisions. So you can make this really, really fast, which is why modern Ethernet, you'll hear terms like 1 gigabit switched Ethernet. The switched part refers to the fact that the single network is implemented by connecting all of your interfaces on the subnet to a switch device. Okay, so this switch has 6 interfaces. And so the question then is, how does the switch know that host at MAC address A prime is reachable via interface or port number 4, and that B prime is reachable via port number 5? How does it know that these MAC addresses, A prime and B prime, are reachable through their respective ports on the switch? Well, that's a great question. Each switch has a switch table entry, and that switch table entry contains 2 pieces of information: a MAC address of the host, the destination MAC address, and the interface in order to reach the host. Now, of course, you want this thing to be dynamic and plug and play, so you also include a timestamp, and that timestamp acts like a TTL field. Once that timestamp has expired, it repopulates that entry in the switch table. And so this looks a lot like a routing table, only it deals with destination MAC addresses, not destination subnets. All right, so how are these entries created? Something like a routing protocol? Not quite. It acts a little bit more like a NAT box than like a routing protocol. So a switch does what's called self-learning. The switch learns which hosts can be reached through which interfaces based on the source MAC address for which that frame made ingress to the switch device. So when the frame is received by the switch, it writes down the port on which that frame was received, as well as the MAC address that was the source MAC address. Because if the source MAC address sent it inbound on that port, that ingress port, then it knows that that port is where it will find that particular MAC address. And so it records these sender locations and port number pairs in the switch table, and that's how it populates entries that are used for forwarding these frames across the switch from its buffers. So let's take a look at an example. Let's say host A at MAC address A wants to send a frame to a host at MAC address A prime. So we have the source address is the MAC address for A, and the destination MAC address is the destination MAC address for A prime. So A then sends its frame to the switch, it arrives on port 1 or interface 1 on the switch. So the switch writes down in its switch table, MAC address A is reachable on interface 1 with a time to live field of say 60 milliseconds or 60 seconds. So now it knows that the destination MAC address is A prime, but it doesn't have an entry for A prime. So what it does is the following scheme. You record the incoming link and the MAC address of the sending host, because that MAC address can be reached along that link. And so then you index into or search your switch table trying to find the MAC address for the destination interface. If you find an entry, you go ahead and forward down that segment. Otherwise, you perform flooding. And when you perform flooding, a copy of that datagram gets sent on every port. And so if you send on every port, one of them will be the correct destination. It will get it and send back a response. And say if you're using TCP, you get an acting in the direction. So eventually, what was the destination is going to send back a reply. All right. So let's take a look at this self-learning and forwarding example. And so here we have host A is the source MAC address, and A prime is the destination MAC address. A sends this frame into the switch. It arrives at the switch. It writes down, okay, well, this came in on interface 1, and the source of this frame coming on interface 1 was MAC address for host A. So write that down with the time to live field. So then it looks into the switch, looks into its switch table, and it finds that there is no entry for MAC address A prime. So it goes ahead and it floods, sends a copy out on every link, except for that link from which it originated. So now when it sends it along that link via flooding, all of them, C prime, B prime, C, and B, say, well, that's not my MAC address. I can't be the destination, except MAC address for host A prime says, oh, wait a minute, that's my MAC address. I'm going to go ahead and I'm going to pull that frame into memory, and I'm going to unwrap the datagram as payload stored inside. So then, at some point, A prime is going to send back a response to A. And when it does so, it's A prime sends it into the switch, and the switch records, okay, well, I got this from source address A prime, and it came in on interface 4. So it writes down interface 4 is where I can find MAC address for host A prime, and let me put a time to live on that, an expiration date. So now it then looks up the destination MAC address A, and it finds, lo and behold, there is an entry for destination MAC address A. It's interface 1. So it sends it selectively through interface 1, and it gets to host A. Host A sees that, okay, well, that's my MAC address as a destination. Let me pick up that frame, and I will unwrap the payload, which is the datagram, send it up to my network layer, which will then send it to the transport layer and deliver to the application. Okay, and so this is our self-learning, and this is completely plug and play. The switch populates its switch table, and when the time to live field expires, it engages in that repopulation again. All right, so that's all I had for today. So we'll end there, and we'll pick back up next time as usual. Please stay healthy, stay safe, and I'll see you all on Thursday.